In this video, we're going to be looking at L'Hopital's rule and indeterminate forms of L'Hopital's rule. This rule you're going to see is very nice when you're working with limits. It enables us to, instead of having to go through some of the algebraic processes we solved limits with in the beginning of calculus, this gives us another rule to help us evaluate certain types of limits. So if we were looking at the limit of ln of x all divided by x minus 1, and we're taking the limit as x approaches 1. Notice if we tried direct substitution, we would get ln of 1, which is 0, all over 1 minus 1, which is 0. So we would get the indeterminate form 0 over 0. In general, if we have a little limit of the form, when we take the limit of an f of x divided by a g of x as x approaches a, where both the numerator and denominator would give us 0, so we would get 0 over 0, then this limit may or may not exist, and it's called the indeterminate form. We learned this early on in our study of limits. Now, whenever we get this type of a limit where we get the indeterminate form, we can apply L'Hopital's rule. We can also apply L'Hopital's rule if we get infinity divided by infinity when we use direct substitution. For instance, if we took the limit of e to the x divided by 5x squared as x goes to infinity. If we use the direct substitution technique, which means what's happening to e to the x as x gets larger and larger and larger, well, that's going off to infinity. And likewise with 5x squared, as x gets larger and larger and larger, the denominator goes off to infinity. Now, we can apply L'Hopital's rule if one or the other is a negative infinity, the other is positive, or both negative, both positive. It doesn't matter the sign. We could still apply L'Hopital's rule. So here's L'Hopital's rule. Suppose f and g are differentiable and g prime of x does not equal 0, the denominator does not equal 0, near a except possibly at a. Suppose that we have the limit of f of x as x approaches a equals 0 and the limit of g of x as x approaches a equals 0, and or the limit of f of x as x approaches a equals positive or negative infinity, and the limit of g of x as x approaches a equals positive or negative infinity. Then applying L'Hopital's rule indicates that if we have the limit of f of x divided by g of x as x approaches a, and we get any one of these scenarios, a 0 over 0, or a plus or minus infinity divided by plus or minus infinity, then we can take the derivative of the numerator divided by the derivative of the denominator. Now, this is not applying the quotient rule. We just simply take whatever's in the numerator and find the derivative. Whatever's in the denominator, find the derivative, and then we can use direct substitution to see if we get our solution. If we get 0 over 0 again, or infinity over infinity again, we can apply L'Hopital's rule again. Here's an example. Back to the one we looked at in the beginning of this video, we have the limit of the ln of x divided by x minus 1 as x approaches 1. If we looked at direct substitution for this limit, we would get the natural log of 1 all over 1 minus 1, which is 0 over 0, which is the indeterminate form So this would equal 0 over 0. So we can apply L'Hopital's rule. Now, L'Hopital's rule says if we get the indeterminate form, 0 over 0, we can then take the derivative of the numerator. So the derivative of the numerator divided by the derivative of the denominator. We're not applying the quotient rule. So we have the limit. Now the derivative of ln of x is 1 over x. The derivative of the denominator, x minus 1, is 1. So we would have the limit of 1 over x as x approaches 1. Now we can use direct substitution. So we would get 1 over 1, or 1. So we have found this limit. Calculate the limit e to the x divided by x squared as x goes to infinity. If we use the direct substitution technique, we notice that e to the x as x goes to infinity, this goes off to infinity. X squared as x goes to infinity, this goes off to infinity. So we can apply L'Hopital's rule because we did get the indeterminate form infinity divided by infinity. So we can take the derivative of the numerator divided by the derivative of the denominator. So we would get the derivative of e to the x is e to the x. And the derivative of x squared is 2x. Now we look at direct substitution again. If we apply direct substitution, e to the x as x goes to infinity, this would go off to infinity. Likewise, 2x goes off to infinity. So we can apply L'Hopital's rule again. And I'll just indicate this means we're going to apply L'Hopital's rule again, since we have our indeterminate form infinity over infinity. So applying L'Hopital's rule again, derivative of the numerator is e to the x divided by the derivative of the denominator, which would be 2, as x approaches infinity. Here we get e to the x goes off to infinity. The limit of 2 as x goes to infinity would be 2. So this would equal infinity, means it does not exist, but the informational limit would be simply infinity. So the limit of e to the x all over x squared as x approaches infinity equals infinity. That's our informational limit. Find the limit of ln of x divided by the cube root of x. If we used direct substitution, ln of x as x goes to infinity, and the cube root of x as x goes to infinity goes off to infinity also. We can apply L'Hopital's rule, which indicates we take the derivative of the numerator divided by the derivative of the denominator. I'm going to write it as x to the 1/3. Now finding those derivatives and then direct substitution, we would get 1 over x, and we would have 1/3 x. Now we're going to subtract 1 from the power, so we'd be subtracting 3/3, so we'd have x to the negative 2/3. Now before we directly substitute to see our result, let's clean this up a little bit. If we have 1 over x divided by, this could be written as 1 all over 3x to the 2/3. We would invert and multiply, so we'd have 3x to the 2/3 over 1. So we have 3 all divided by, we have like bases, our x's have like bases, so we would subtract our exponents. So we'd have x 1 minus 2/3, which is 3. Let me try it down here. 3 over x 1 minus 2/3. This would be 3 all over x to the 1/3 power. So that's what we're working with now. And if we analyze this one, let x to the 1/3, as x goes to infinity, that's just going to get larger and larger and larger. So the denominator is getting larger, the numerator is staying at a constant, so this whole thing is going to go off to 0. So our conclusion is the limit of the ln of x all over the cubed root of x, as x goes off to infinity, we say equals 0. Find the limit of the tangent of x minus x all over x cubed. And we're taking the limit as x goes to 0. So first, let's take and use direct substitution. Tangent of 0, 0, minus 0 all over 0. We get the indeterminate form 0 divided by 0. So we can apply L'Hopital's rule. So we will take the derivative of the numerator divided by the derivative of the denominator. So derivative of tangent, secant squared x minus 1, all divided by 3x squared as x goes to 0. If we use direct substitution, the secant of 0 is 1. 1 squared is 1, so we'd have 1 minus 1. We get 0 over 0. So at this point here, we get the indeterminate form again, 0 over 0, so we can apply L'Hopital's rule again. Now if we take the derivative of the numerator, you may say, well, I see a trig identity there. You may be able to use a trig identity. Secant squared x minus 1 looks like it would be tangent squared x. But if we just took the derivative, it would be 2 secant x times secant x tangent x. That's applying the chain rule. And then derivative of 1 is just going to 0. All divided by 6x. And we're going to take the limit as x approaches 0. And if we use direct substitution, again, we get 0 over 0, because the tangent of 0 is 0, so this whole numerator would go to 0. So if we apply L'Hopital's rule again, we have in the numerator here, it's 2 secant squared x times tangent x. So if we apply L'Hopital's rule again, we would have the first times the derivative of the second plus the second times the derivative of the first, which would be 2 secant x, and then the derivative of the inside function would be secant x tangent x, and the derivative of the denominator is 6, and we're taking the limit as x goes to 0. Now if we evaluate our secants, secant of 0 we said is 1, 1 squared 1, 1 times 1. So we would have 2 times 1 plus, now here tangent is going to go to 0. So regardless of what's in this quantity here, it's going to 0. Then we have over 6, so we'd have 2 over 6, or 1/3. Find the limit of the sine of x divided by 1 minus cosine of x as x approaches pi from the left. If we use direct substitution, the sine of pi, as x approaches pi from the left, we can use direct substitution. We would get the sine of pi is 0. 1 minus cosine of pi would be -1. So we'd get 1 minus -1, which is 0 over 2. We don't need to apply L'Hopital's rule. We did not get 0 over 0, or infinity divided by infinity. This value right here is the value of our limit. That just equals 0. Now, if you went through this problem and you just applied L'Hopital's rule without checking to see if we got the indeterminate form, you may get an answer, but it would be incorrect. Now we're going to be looking at indeterminate products. We looked at the indeterminate form 0 divided by 0 and infinity divided by infinity. Now we're moving to another type of indeterminate form. So if we take the limit of f of x as x approaches a, that equals 0, and the limit of g of x as x approaches a equals infinity or negative infinity, what is the value of the limit of f of x times g of x as x approaches a? We would get 0 times infinity. This is not the indeterminate form 0 over 0 or infinity over infinity. So we would not be able to apply L'Hopital's rule at this point. But we may be able to rewrite one of these functions as 1 over x and put it in the denominator, and that would still be equivalent. So here, if I said I'm going to rewrite this as g of x divided by 1 divided by f of x. Well, if we invert and multiply, we would get back f of x times g of x. But what is the result here? If g of x is going off to infinity, it says that right here. Now, if we looked at the limit of 1 divided by f of x as x approaches a, well, if f of x is going off to 0, that means the denominator is getting larger and larger and larger and larger and larger. So that would be going off to infinity also. Now we could apply L'Hopital's rule. And it doesn't matter if I take f of x divided by 1 divided by g of x, or leave g of x in the numerator and then take 1 divided by f of x to the denominator. But you can see we would either get infinity over infinity, or if we did it the other way, we would get 0 over 0. Because if I took the limit of f of x divided by 1 over g of x, here we can see that the numerator, well, it says the limit of f of x as x approaches a equals 0. So that would be 0. And if the limit of g of x as x approaches a is going off to infinity, if this is going off to infinity, well, this whole thing would be getting smaller and smaller and smaller. It would be going to 0. So we rewrite the product as a quotient, and then we could apply L'Hopital's rule because we get the indeterminate form 0 over 0 or infinity over infinity. And here's an example. If we have the limit of x times ln of x as x approaches 0 from the right, first off, we're going to look at, if we directly substitute, we would substitute 0 in for x, we would get 0. And then if we look at the limit of the ln of x, here's ln of x, as x approaches 0 from the right, you can see we're going off to negative infinity. So we would have 0 times negative infinity. So that's the indeterminate form, 0 times infinity. So we're going to apply this rule. I'm going to leave ln of x in the numerator and then take and rewrite x as 1 over x in the denominator. Now if we use direct substitution, we would get negative infinity. The limit of ln of x as x approaches 0 from the right. It's going off to negative infinity. And if you graphed 1 divided by x, it looks like this. So as x is going to 0 from the right, we can see that's going off to infinity. So now we can apply L'Hopital's rule. So we're going to take the derivative of the numerator, which would be 1 over x, derivative of the denominator. Now remember, if we take the derivative of 1 over x, which is x to the negative 1, we get negative x to the negative 2. So that would be negative 1 all over x squared. Now, before we directly substitute, let's rewrite this, simplify that fraction. So we would have 1 over x, and then we're going to invert and multiply. So we'd have times negative x squared over 1, and that reduces down to negative x as x approaches 0 from the right. And now we can use direct substitution. We can see that would be 0. So there's our limit. We have found that the limit of x times ln of x as x approaches 0 from the right equals 0. Indeterminate differences. Now, it's a good idea to keep track of all the different types of indeterminate forms we're looking at. But the most important one to remember is that if we get 0 over 0 or infinity over infinity by evaluating those limits, we can apply L'Hopital's rule. These others, we get a different form, but then we try to rewrite them so we get 0 over 0 or infinity over infinity. So the first one that we looked at was if we get 0 times infinity. We know how to rewrite that one now, so we get 0 over 0 or infinity over infinity. Now this one here, the indeterminate differences. Let's just think about if we're evaluating a limit and say we get infinity times infinity. Couldn't we make the conclusion that if we have a very large number times another very large number, the result is going to be infinity? Same idea if we have infinity plus infinity. Well, if I have one large number and adding another large number, it's going to be another large number. However, infinity minus infinity, we are looking at two different rates of changes here. This one may be going off to infinity at a different rate than this one is going off to infinity. So we can't make the conclusion that this is 0 or 1 or any other value. We don't know because one of them may be going off to infinity faster than the other. So we could get anything as an answer for this form. So this is called the indeterminate difference. So you can see we have this situation, which if we get either of those, we know it's infinity. This one, we're going to have to do some exploring. And then the last, if we looked at infinity divided by infinity, well, we know we're going to use L'Hopital's rule. So those are the different cases we're going to be looking at. And so we have to figure out what's going on here if we have indeterminate differences. How are we going to take care of that? All right, so what we're going to do is we're going to try to rewrite in terms of a quotient or factor something out. There's a couple of different techniques, but one of them is to rewrite in terms of a quotient. So then we may get our 0 over 0 or infinity over infinity. An example of this one. If we want to compute the limit of the secant of x minus tangent of x as x goes to pi by 2 from the left, if we used direct substitution for this one, we would get infinity minus infinity. This would give us infinity minus infinity. And if you think about the graphs of those, this one you're going to be thinking the secant graph is created from the cosine graph, and at pi by 2 you're going to be looking at what's happening as we approach pi by 2 from the left, and we would have an asymptote where it intersects the x-axis, so the secant graph would be going off to infinity. And if you think about the tangent graph like this, here's pi by 2, and so as x approaches pi by 2 from the left, we're going off to infinity again. So that's why we get infinity minus infinity. Now if we write each one of these using trig identities, secant of x is 1 over cosine, tangent is sine of x over cosine of x. Now look at what happens when we combine these, because we have a common denominator. And if we used direct substitution at this point, what would we get? Well, we would get 1 minus. Now the sign of x, as x approaches pi by 2, the sign of pi by 2 is 1. And then the cosine, the limit of the cosine of x as x approaches pi by 2 would be 0. So now we get our indeterminate form, and we can apply L'Hopital's rule on this form right here. So if we apply L'Hopital's rule, because we do have that indeterminate form, 0 over 0, so we're going to take the derivative of the numerator. So the derivative of 1, that goes to 0. Derivative of sine x is cosine of x. Derivative of the denominator now. So derivative of cosine of x is negative sine of x. So I've got an equal sign in there that I didn't intend to put there. And this is equivalent to the limit of the cotangent of x as x approaches pi by 2 from the left. Now, if you wanted to leave it in terms of cosine and sine, you could to use your direct substitution, because we know that the limit of the cosine of x as x approaches pi by 2, well, if we use direct substitution, we would get 0. And then the limit of the sine of x as x approaches pi by 2, that would just give us negative 1. So this equals 0. So we have found our limit, the limit of the secant of x minus tangent of x as x approaches pi by 2 from the left equals 0. Indeterminate powers. Now we have several different indeterminate powers that we need to look at. And these arise from the limit of an f of x raised to the power of a g of x. Here are the indeterminate powers we need to be familiar with. If we get 0 raised to the 0 power, infinity raised to the 0, or 1 raised to the infinity power. Each of these can be rewritten by taking the natural log. Now this is going to look familiar to something that we've done previously when we were taking derivatives of the form f of x raised to a g of x. We took the natural log of both sides. And that allows us to bring the function g of x out of the exponent. So here's an example. Calculate this limit. If we looked at direct substitution for this one, if we directly substitute in 0, we'd have 1 plus, now sine of 0 is 0, cotangent of 0 is infinity, so we would get 1 to the infinity power. Now let's look at, if we want to find the limit of this function, we're going to say, well, the limit equals y. So if we said that we're going to take the natural log of both sides and then we'll take the limit of each side as x goes to 0 from the right. Now the limit for each side, notice that we are able to rewrite cotangent as 1 over tangent of x. And if we then took the derivative, if we looked at direct substitution first, let's go ahead and show that step right here. If we use direct substitution, we'd have ln of 1 plus sine of 4 times 0. So we'd have ln of 1 all over tangent of 0, which is 0. So you can see we get the indeterminate form. That's why we can go ahead and apply L'Hopital's rule in this next step. Now, remember the derivative of the numerator. If we're looking for the derivative of ln of 1 plus the sine of 4x, the general rule for the derivative of ln of u is u prime over u. So we would take the derivative of, let me put another parenthesis here, the derivative of the inside function, and that would give us 4 cosine of 4x. And then all divided by u, which is our 1 plus sine of 4x. So that's what we have in our numerator here. And then the derivative of the denominator, secant squared x. Now looking at, if we look at now this side of our, just to here, if we look at this piece now, if we use direct substitution on this side, we would have the limit of 4 times cosine of 4x. We'd plug 0 in for x, so we'd have 4 cosine of 4 times 0, which is, and then we'd have all over 1 plus the sine of 0 divided by secant of 0 squared. Now in the numerator, cosine of 0 is 1, so we'd get 4. 1 plus sine of 0, we'd have 1 plus 0. And then the secant of 0 is just 1, so we'd have 1 squared. And you can see this is just 4 over 1, or just 4. So that's what the right side equals. Now notice here, we still have this limit over here. We're trying to solve for y. We want to know what y equals. So if you rewrote this in exponential form, or you can think of it this way. Let me write this out. We have right now the limit of the ln of y as x approaches 0 from the right equals 4. And I forgot my limit. The limit as x approaches 0 from the right of 4. Now we can take and either rewrite this in exponential form, or you can just say I'm going to raise each side to the base e. Now we can take the limit outside of raising this to the base e, and then we're looking for the limit of e to the ln of y. But e to the ln of y is y. And the limit of e to the fourth as x approaches 0, and that's just a constant, is e to the fourth. So now we can finish the problem and move on to the next one. Example. Find the limit of x raised to the x power as x approaches 0 from the right. Now we would apply, again, we have an f of x raised to the g of x. So we're going to set this equal to y because we're getting the indeterminate form 0 to the 0 power. And this is using a little bit different technique than what we used in the last problem. I'll go ahead and finish this out here. So we have our limit of ln of x, and finally we get our limit equals 1. Now if we backed out of this and used the other technique that we looked at in the last problem that we did, we would say y equals x to the x power. So ln of y equals, now when I take the natural log of this side, now I can bring down the x, and now we can take the limit of the natural log of y as x approaches 0 from the right equals the limit of x ln of x as x approaches 0 from the right. If we looked at the limit of the right side, if we use direct substitution, we get 0 times negative infinity. So we're going to rewrite this one as ln of x all divided by 1 over x as x approaches 0 from the right. And then we will, now if we use direct substitution, we'd get infinity, negative infinity over infinity. So now we can apply L'Hopital's rule. So we'd get the derivative of the numerator divided by the derivative of the denominator. And here we did this problem earlier, and we saw that we got negative x here when we simplified that. And so we would have the limit of the natural log of y as x approaches 0 from the right equals 0. Now if we let's move back up here now. if we take and rewrite this in natural log of y as x approaches 0 from the right, and we raise each side to the base e, we would now have the limit of y as x approaches 0 from the right equals 1. Now the limit of y as x approaches 0 is still going to be just y, so y equals 1. So there's two different ways we can go about solving it.